Welcome to the session on variable acceleration, constant acceleration formulae. The objectives for this session are to derive constant acceleration formulae using calculus. We're now going to take a look at displacement, velocity and acceleration and see how they relate to each other in terms of integration and differentiation. So first, let's take a look at displacement. Suppose displacement s of t is a function of time. Then velocity v of t is ds dt, since velocity is the change in displacement over change in time. And acceleration, a of t, is dv dt, or this can also be expressed as d2s dt squared, since acceleration is the change in velocity over change in time. So if we begin with displacement s of t, we differentiate to obtain velocity v of t, or this can be of course expressed as ds dt. And if we differentiate again, this can either be written as dv dt or d2s dt squared, and this is of course the acceleration a of t. Now the reverse of this, say if we begin with acceleration a of t, we can integrate now to obtain v of t equals integral a dt. And then if we integrate velocity, then we obtain displacement. So s of t equals the integral of v dt. So to summarize, s of t equals the integral of v dt, velocity v of t equals ds dt, or v of t equals integral a dt, and acceleration is dv dt, which equals d2s dt squared. We are now going to use calculus to derive the formulae for motion with constant acceleration. Pause the video and have a go at this example. Press play when you're ready to view the solutions. Let's now tackle example 1 part A. A particle moves in a straight line so that it has constant acceleration a meters per second squared for t greater than or equal to 0. If its initial velocity is u meters per second and its original displacement is 0 meters, prove that at time t its velocity v meters per second is given by v equals u plus at. So let's solve this. We have from our formulae that v is equal to integral of a dt, and therefore if we integrate this expression we have at plus a constant c. Now from our example we know that when t equals 0, v is equal to u, which is of course the initial velocity. Therefore, if we plug in t equals 0 into this equation, here, we obtain u equals c. And therefore, v equals u plus at. Now let's take a look at part B. We have the same scenario, of course, but this time we're required to prove that at time t, the displacement s meters is given by s equals ut plus a half at squared. So let's solve this. Now from our formulae, one which has been highlighted is s equals the integral v dt. So since from part A we have that v equals u plus at, we can plug that in place of v, as shown here. And then integrating this gives us ut plus a half at squared plus the constant of integration. But when t equals 0, we have that s equals 0 also. And therefore, plugging these values into our equation for s, as shown, will help us find the constant of integration, which is of course 0. And therefore, s equals ut plus a half at squared. This brings us to the end of this session. If you have understood its contents, you should be able to derive constant acceleration formulae using calculus. Thank you very much for listening. To understand this topic in greater depth, do attempt the exercises in your textbook related to this topic.